Hello friends, welcome to Learn Easy. Today in this session, we will discuss strain energy, modulus of resilience and modulus of toughness. Strain energy is the internal energy stored in a deformable body when it is subjected to an external load. The work done by the external force to deform the elastic body is equal to the strain energy stored within it. This energy is fully recoverable if the material remains within its elastic limit. Strain energy per unit volume is strain energy density. Now, let us examine the stress-strain curve of a ductile material with linear stress-strain relationship obeying Hooke's law. This is the stress-strain curve of a ductile material. Up to point A, stress is directly proportional to strain. This is straight line. So, stress divided by strain is constant. This constant is called Young's modulus. Denoted by E. Now, at point X, stress is sigma x and strain is epsilon x. So, sigma x divided by epsilon x is equal to E, Young's modulus. After point A, strain increases relatively more than stress, and at point B, strain increases at lower stress. That means the material yields at point B. B is called yield point. This continues up to point C. From C to D, strain increases in higher rate compared to increase of stress rate. Again, from D to E, strain increases with lower stress. Finally, at E, the material fractures. So, E is the fracture point. And this point D is called ultimate strength. The blue hatched area is called modulus of resilience. This area. And the red hatched area, the whole area, is called modulus of toughness. Now, modulus of resilience UR is equal to sigma of yield point sigma y square divided by 2e. Where sigma y is yield strength and E is Young's modulus. SI unit of modulus of resilience is joule per meter cube, or joule per meter cube is called Pascal. Now strain energy U is equal to half F del, where F is applied external force in Newton, and del is resulting deformation in meter. Unit of U is Newton meter or joule. This is the general formula of strain energy. Now, formula based on stress strain can be derived from this general formula. E is equal to half F del is equal to half F is equal to sigma stress is equal to F by A. So F is equal to sigma A into del. Del is strain is equal to del divided by original length. So del is applyation into L. So we can write half sigma A into applyation L. This is half sigma into applyation into A into L is equal to half sigma into applyation into V. So, based on stress strain, we can write U is equal to half sigma into epsilon into V, where sigma is stress, epsilon is strain, and V is volume. Again, we can write U is equal to half sigma into sigma by E into V. E is equal to stress by strain. So, epsilon is equal to sigma by E is equal to half sigma square into V divided by E. This is another formula we can use. E is equal to Young's modulus. For axial loading, tension or compression, suppose this is a rod which is subjected to tension. For a circular shaft of length L, and cross-sectional area A, under a load F, strain energy U is equal to half sigma epsilon into V. So half sigma we can write A by A into epsilon del by L into V is A into L. A cancel, LL cancel. So we can write U is equal to half F del where del is deformation, L is original length, F is applied force. equal to half F del is equal to half F E is equal to stress by strain is equal to F by A divided by del by L. So from here del by L is equal to F by A into E, or del is equal to F into L divided by A into E. If we put this del is equal to F into L divided by A into E here, it will be F into L divided by A into E. So again it will be half F square into L divided by A into E. So we can write U is equal to F square L divided by 2AE. This is another formula we can use. Now in case of torsion, suppose there is a circular shaft which is subjected to torsion. Length of the shaft is L. A shaft of length L subjected to a torque T, strain energy is equal to T square into L divided by 2G into J, where T is equal to applied torque G is equal to modulus of rigidity L is equal to length of shaft and J is equal to polar moment of inertia. For round circular shaft, polar moment of inertia is pi R4 by 2. Is equal to pi D4 by 32. So D is the diameter of the shaft. In case of torsion, we can write U is equal to half T theta, where T is applied torque and theta is angle of twist. Polar moment of inertia is a measure of an object's resistance to twisting. It is a geometrical property of a cross-sectional area. Polar moment of inertia is J for round section is pi r4 by 2 or pi d4 by 32. Now in case of bending, U is equal to integration of m square divided by 2EI. Limit is 0 to L. Where L is length of the beam, which is subjected to a bending moment M. E is Young's modulus. And I is second moment of area or this is called area moment of inertia. Moment of inertia for this rectangular shape, Ix is equal to B H cube by 12. Similarly, Iy is equal to H B cube by 12. Round shape, Ix is equal to Iy is equal to pi by 64 d4. for spring, strain energy U is equal to half K del square, where K is spring constant. Is equal to F by del, where F is applied force to the spring. And del is the deflection of the spring. Now, modulus of toughness. The modulus of toughness indicates the total energy that can be absorbed by the material per unit volume up to the point of fracture. The total area up to the point of fracture under this stress strain curve is modulus of toughness. So we can write modulus of toughness UT is equal to integration of sigma into d application. Limit is application fracture and 0. This is sigma into d application, and limit is application fracture, this sigma into d application, limit is 0 to application F, application fracture. Here application fracture, strain at fracture point, and sigma is equal to stress at fracture point. SI units of modulus of toughness is joule per meter cube or Pascal. That's all for today. Thank you.